Hey everybody, how's it going? My name is Attila, and in this video we're going to talk about cosine similarity, how it works in pgvector, and just in general how cosine similarity works. I think if you are working with embeddings, text embeddings specifically, you will definitely need to understand cosine similarity, because in most of the cases this is the similarity function that you will have to use. Let me show you an example. So let's say we are working with these two vectors. We have a green vector, a blue vector, and we are trying to figure out the cosine distance between these two vectors. And what that will calculate is the angle between these two vectors. So this is very important, because when you're calculating the cosine distance or the cosine similarity, you don't care about the length of the vectors, or in other words, you don't care about the magnitude of the vectors. So the magnitude doesn't matter. It's not gonna be part of the result. It only cares about the angle, or you can also say it only cares about the difference in directions between the vectors. So that's a very important point, because there are other similarity functions, for example, the dot product similarity function, that also includes the magnitude. So that will also be an important factor in the calculation. Here, we just only care about the angle. Now let's quickly look at the formula. So if you want to calculate the cosine similarity of two vectors, you first need to calculate the dot product of the two vectors. And dot product is actually a similarity function in itself. You can use it as a similarity function, but in this case, it's just part of the formula. So you get the dot product, which is going to be one value, because it's a scalar product. So there is only one value that you get as a result of this calculation. Then you calculate the dot product of the magnitudes of the vectors. And magnitude, again, means length of the vector. You divide these two values, and that's going to be your cosine similarity value or metric. Now in Postgres, when you use pgvector, you are going to work with the distance metric, not the similarity metric. And you can get the distance metric by simply subtracting the similarity value from 1, which will give you a distance metric between 0 and 2, and the similarity metric is always going to be between -1 and 1. So for example, if the result of the similarity calculation, the cosine similarity calculation, is 1, the distance will be 0. And what that means is that the two vectors are completely identical when it comes to the cosine similarity. Again, there could be a difference between the magnitudes between the vectors, but cosine similarity doesn't care about that. If you just calculate the dot product, which is again this one, that will also include the similarity or the difference between the magnitudes. But in the case of cosine similarity, we just care about the angle. Now, if the similarity is 0, that means that the distance will be 1. And as far as angle, that's going to be a 90-degree angle between the two vectors. And what that means is that the two vectors are completely unrelated, so they're not similar at all. Now, if we look at the last option, the other end of the range, -1, similarity is -1, distance will be 2. In this case, the angle between the two vectors will be 180 degrees. So the two vectors are opposite of each other in terms of similarity. Now let's look at the implementation of this function within Postgres. There's a vector cosine similarity function that you can find in the pgvector source code. Here's the link to the file on GitHub, and let's see how it works. So if you look at the variables, we have 3 variables here. We have similarity, norm A, and norm B. So similarity will be basically the dot product of the vectors, which is, as you remember, part of the formula. Let me bring that up just so we remember. So similarity will be this part of the formula at the end of this implementation. And then we have norm A and norm B. So norm is just another word for the magnitude of the vector. So norm A and norm B will be these parts of the formula. Going further, we have a for loop here, which is needed to iterate over each value in the vectors. And as you can see, we have this variable here, which indicates the dimensions of the vector. Because remember, even though we only have two vectors, those vectors can have 2 dimensions, 512 dimensions, 1000 dimensions. So we have multiple numbers that we need to iterate over. So within this loop, first we are doing the calculation for the dot product. So this part is just doing that. Now the other part, the norm A and norm B calculations, are following this formula right here, because this is calculating the magnitude of the vector, and for that we need to square the number, sum them all up, and then take the square root. So we are doing the squaring part here. This is where we are doing the summing up, and then in the return statement, that's where we are actually doing the square root part. One minor implementation detail that you can notice in the comments here as well is that normally you would calculate the magnitude of vector A, then you would calculate the magnitude of vector B, and then you would just do the multiplication. But here we just we do the multiplication first, as you can see here, and then we are taking the square root of that number. And the reason for this is probably because it's more efficient. Instead of doing square root operation twice, here we just need to do it once, so it will be probably more efficient this way. And so finally, putting it all together, once you have the multiplication of the magnitudes of the vectors and you have the similarity, which is the dot product of the vectors, you can return the cosine similarity of the vectors. Now remember that pgvector is working with distances, so when you run the cosine operator or the cosine similarity operator in pgvector, that's actually going to return the distance. So there is an additional function that gets executed after this, which is going to be the cosine distance function, but this is much more easier to understand. So let's quickly go through this function as well. So again, we are working with two vectors here. We have vector A, vector B, and then we have a similarity variable here. Now this similarity variable will actually be the output of the vector cosine similarity function that we have just looked at a second ago. So this is not going to be the dot product of the vector. This is the actual similarity metric. And then you can actually see at the end what is returned from this function, which is using the same cosine distance calculation that I just showed you before. You are subtracting the similarity metric from 1, and that's going to be the distance. Now, one extra implementation detail here is this part. This is just making sure that if you have a similarity value that is larger than 1 or smaller than -1, then it just brings that number back to the range. Now, why do you need this part? If you look at the math behind the cosine similarity function, it's not possible to return a number that is smaller than -1 or larger than 1. My current understanding is that it's just trying to avoid the rounding issue, because we're working with float precision numbers here. So you might have a situation where the actual value that is stored in the database is going to be bigger than 1. So you might get like something like 1.00002 as the actual value, which is technically bigger than 1, but It's just a rounding issue. So that's my current understanding, but if there's another reason for this implementation, you can let me know in the comments. So that's all I had to share today, and I see you in the next video. Bye.